Hey everybody, so here's our final CS302 assignment for the semester, this one's going to be a graph theory program, and we're going to the idea of this program is we're going to be given a graph which will serve as a family tree. So it's going to be a directed acyclic graph, and we're going to try to find all the ancestors of every single person in our family tree. So this first paragraph here basically just going over, I guess, sort of a little shout out to assignment 7, how everyone's brain has been fried from assignment 7. So this one will be not really as complicated conceptually. So instead of, doing this much worse and having maybe a cousins list you'd have to find, or, I could have made this a lot worse, but I decided to make this a little bit of a simpler problem. So find all the ancestors of a node. So basically the first thing we're going to have to do is go over the input file, which is going to contain all of our edges in our graph or in our family tree. Okay, so a bright light flash warning coming up. So this is going to be our first file we're going to use. So basically each line of this file is going to be an edge. So we use strings to sort of label each node. So right here in this first line, this implies we have an edge from the node labeled 2 to the node labeled 4. And next line we have a node labeled 3 has an edge to the node labeled 7, and so forth. So what we're going to have to do in this program is first be able to just construct our adjacency list. So sort of using this array of linked lists as I described in class earlier this semester when we covered graph theory is going to be the way to go. But luckily for this assignment we can use all STL containers. You don't have to create pointers or have to create sort of your custom containers. You can use these built-in ones just to make this last assignment just that much more easier. So this structure I have defined right here. I don't think you can see the mouse in this, but I'm going to highlight this. This is going to be your adjacency list, and it looks really like a lot of weird stuff going on here, but let's look at this though. It's going to be an unordered map because, well, unordered maps are fast. Now, of course, if you want to use a map instead, because you're going to have to output the names in sorted order, you can use a map instead because a map is going to have everything ordered. But I really feel using an unordered map is better because it's a faster lookup time. And of course, you can always insert all the names, all the key values of each entry in your hash map into a vector, and sort that is a better idea than using a map, but it's up to you though. So anyway, and also a map has it works the same way. You use a bracket operator to look up something, and then you assign it using the value fields or using the equal sign. So it's the same way it works to look up an element in an unordered map or an ordered map. So I think just map is the name of the ordered map type. So anyway, over here we have our unordered map, and our key type is going to be a string. So obviously it's going to be a person's name or a node, and it maps to a list of strings. So a list in C++, in that you have to include lists in your program, it basically is going to just be, how shall we say, it's going to be a linked list. So you don't have to create your own custom linked list. There actually is a linked list in C++ STL. I bet you would have liked to have been able to use this, whenever linked lists were used in 202 or 302, but I guess the idea is that you had to learn how to use linked lists earlier, and now that we know how linked list works, we can of course use the one that's given to us in STL. So basically we're going to map a person's name to a list of their neighbors, or in this case a neighbors list is going to be really that descendants list. So what you want to do is you have to insert each person. So for example, if like I gave some code right there, if you want to be able to insert all of Bob's neighbors or descendants into a list, you use this structure, adjacency list, and then Bob will be the search type, and then dot pushback will insert Janice into Bob's neighbors list. Then of course you can do adjacency list Bob, we insert Marty, so we're going to have Janice and Marty are two neighbors slash two descendants of Bob. And of course, Bob, we're going to insert Patrick. So, you know, what was it, Janice and Marty, who are the fake parents of Patrick in that one episode of SpongeBob. So that's what, I think that's why I use these names right there. So anyway, this is going to assign, so the three neighbors of Bob will be Janice, Marty, and Patrick. That's how we just insert these names. And it makes sense because think of the person's name as an array sort of index, if you will. And this returns a linked list object, which then of course we can use that pushback function, which will insert something to the back of that linked list. So I can of course draw this out when we go over parsing the file in a little bit, but you know, that's how we can see this. And of course, if you wanted to traverse through all the descendants or all the neighbors of Bob, well, this code right here will do that for you. So I use the auto type right there, auto descendant equals adjacency list bob.begin. So this begin function returns an iterator to the first node in this linked list. Then we will traverse while it's not equal to the end, which will be that null pointer. And then of course descendant plus plus. And then of course we output it. So I'm just outputting right now, but star descendant is going to output a name. So this code will output Janice, Marty, and then Patrick, because star descendant is going to retrieve that name or that string stored in that node that this descendant iterator points to. So remember back from we went over that start operator back for assignment 1, that returns just that it returns just that list, that field of inside that node. And of course, this descendant is of type standard list, standard string iterator, but I just sort of decided to, you know, use auto instead to avoid this. But of course, a descendant would be of type list iterator. So let's first go over how to parse this file and how to actually visualize its structure on an actual unordered map. Alright, so I'm going to kind of walk you through how to parse this file and how to sort of insert them so we can actually see how the adjacency list looks like after every insertion and so forth. So first, I'm going to include all of our libraries we're going to need to use. So of course, we're going to have to use unordered map. Then we're going to include list, because we're going to have to use a linked list for this. And of course, we're going to have to include IO stream, include file stream. I guess I'll have to also include, I think it's called SS stream. I think that's what the actual type is, but I'll double check on that if I'm wrong with this. So yeah, so we'll need unordered map, we'll need a linked list, IO stream, file stream, I guess. This will need a string stream once again, because that will be useful when we actually want to parse that line after using getLine. And then of course we're going to have include, I'll just have string just to be safe, so we have all of our libraries so far included. So I'm going to have my int main. I'm going to have standard unordered map, standard string, and then standard list, standard string. I'll call it, I guess I'll call it fam tree, I guess. I'll just give it a more appropriate name because it is a family tree after all. Then I'm going to just create my standard IF stream. I call it in file. I'm going to go ahead and just kind of hard code this by just using, I think I call it file fam01.txt. So I'll have to, like, you know, parse. I don't want to read from the input because I would just you know, use the file name we're going to parse from. Let's go ahead and just for now go ahead and create our string, I guess, line. I'm going to go ahead and also call one called part of line. So of course, as always, if you go ahead and say string, or sorry, standard get line, so I think it goes in file first and then line. This reads in that entire first line. So it's going to read in this whole, let me just zoom in on this a little bit. It's going to read in basically all of that, obviously. And then what we're going to do is we're going to basically sort of parse this by using a string stream. So I'm going to say standard, I think it's called string. I can't remember the actual type. Let me see. I think it's, I'll just double check this. I think it's called string stream. Doesn't look right actually. Let me just yeah, I think I'm gonna go with this for right now. Okay, I'm gonna go with, yeah, this is, I don't know why I don't want to go to my notes because I don't want to go to my actually worked out solution right here in front of us. So I'm gonna try just this for right now. Let's see if this actually compiles. Let's just first check this out. So g++ test file. Oh, that actually worked. Wow, I'm actually surprised. Okay, I mean, I totally knew it was going to work, so I'm not surprised at all. So return 0. So, okay. So what I'll do right now is I'm going to have the following loop. So while part of line, I'm going to simply just output part of line / n like that. So we can actually use this operator, this input operator on a string stream, which will basically, as always, is going to break it apart by white space. So there's going to be a white space that separates this arrow from the from and the to. So of course you could have, you know, the name of the person could actually have a space in it. So you have to kind of, you know, parse it and break apart everything by, you know, by space until you finally hit this character right there. Or you can do an actual like string, you know, find this character using a string find function, and you can do that as well. But I found this way to be useful for myself. So I'm going to go ahead and just now compile this once again. Sorry, test file is the what we're using right now. Main was the actual source code. So we can see here, it did break it apart because we first read 2, then this this arrow symbol, and then 4. So they're able to break it apart into those. Now, of course, if let's say the person's name has let's say more than, let's say 225, let's say for some reason I had it like this, then if I were to run this again, it would read 2, then 5, and then this symbol, and then 4. So of course, you can sort of string concatenate. You can concatenate 2 and the 5 together until you finally see this symbol. So for now, I'm going to go ahead and just sort of remove this. But of course, you can just do a simple string concatenation, concatenate all of those strings together until you see this symbol. So for right now, just because I can kind of assume that they're going to be just sort of a string followed by this followed by 4, I'm going to kind of hard code this right now. But of course, you can use a loop that will keep on getting each substring out of this line until we finally hit end of line. So while this is true, it'll hit the end of the line. But for now, we'll just go ahead. I'll let you kind of, you know, figure out how to make this work if you have a compound name. We have more than one word in the name. Let's say you have, like, you know, John Smith would be a name. You have to be able to parse John and Smith into the from, and then the arrow, and then of course, let's say you have like John Smith goes to Chris Jones. Then you have to get Chris and Jones and concatenate those two into one destination. But anyway, let's go ahead and just do it like this for right now. So I'm going to basically just go ahead and I'm going to go ahead and say, I'm going to go ahead and actually call this, maybe for now, I'm going to create another string variable here. So string from and then to, just to make this easier. So I'm first going to get from, then SS, I guess I would say part of lines is going to be kind of a throwaway, and then string stream 2. And of course, you go into our family tree, so fam tree from dot push back to. So let's go ahead, and I'm actually going to do this for every single line. So I'm going to have the following. Let's say while this, I'll do it for every line so we can just get a good idea. So I want to be able to actually show you the contents of our hash map, so you can kind of visualize how this works. I could draw this out, but I'll use the debugger actually to sort of show all this. So I'm going to just one by one, I'm going to extract 2 and then 4, and then 2 goes to 4, and of course extract 3, 7, 3 goes to 7, and so forth. So once I get those from and to names, go to index from, push back to. So I'm going to go ahead. I'm going to use GDB right now so you can kind of see if I kind of zoom in on this. Okay, I can zoom in on this a bit. Okay, let's zoom in on this for right now. I'm going to use GDB to compile so you can see what's the content. So G++ -G test file.cpp, then run a.out. Oh, no, sorry, it's going to be gdb a.out. Runs our debugger. So it's actually not a very elegant debugger, but it's sort of nice enough for simple command line based programming. So I'm going to create a breakpoint. So I want to have the program stop at line 25, so I can actually just sort of check and see what's contained inside my family tree. So I'm going to say breakpoint main.cpp on line 25. So it's going to stop on this line basically once we run our program. So I set up my breakpoint. Oops. Oh, sorry. Oh, darn. Okay. No. My mistake. I suppose I meant to say break test file.cpp 25. There we go. So it creates that breakpoint. I'm going to go ahead and run this. And it stops right there on that breakpoint. So I'm going to go ahead and actually print fam tree. And it kind of shows it's really not the most elegant solution here. But we can see here that for 1 has sort of an edge from 1 to 3. So I can, of course, draw this out in another picture, but we have 1 goes to 3. And then looking at this, 0. So let me just go ahead and actually sort of put these side by side together so we can kind of see this. Let's see if I can do this. Okay, let me try like just do it like that. So anyway, hopefully I'm watching YouTube TV right now. So anyway, right here we have, let's see, so 2 goes to 4 and 7. So we go to index 2. Let's see, where's the next 2? Maybe it got cut off somewhere. Okay, fine. Let's go index 2. There is index 2. Has 4 and 7. So 4 and 7 are the 2 nodes that it goes to. So 2 has 4 and 7. There we go. So basically, it's not the most elegant way of showing it because it's not really as nice as a nice Visual Studio debugger. But this shows us that, so we look at index 1, and it maps to a linked list that contains just this 3 by itself. Index 0 maps to a linked list that contains 3 and 4. These are 2 neighbors of 0. And then index 2 in our hash map contains 4 and 7, and so forth. So you have to go ahead and figure out a way. So let's say if you have more than, let's say you have like the from, let's say we have like John Smith maps to Chris Jones with a space in between. How would we actually be able to parse that line? But it's going to be very much based on this actually. So you have to maybe have a loop right here that runs until we see this arrow symbol, that you know you hit the end of that first sort of name, or the from name. And afterwards, you just kind of keep looping until this kind of string stream with this input operator fails, basically. So that's how you want to think about how to insert elements into your hash maps. Hopefully this part of the video helped you out. So now let's go ahead and talk about how to actually how to think about writing a program to actually find all the ancestors of every single node. So I'm not going to actually draw out that hash map structure. I think in that last video with that debugger sort of displaying of that unordered map gave us a good idea as to how we can visualize it. So of course the bracket, we use a name. Name will essentially be your index of your adjacency list, and it maps to, it returns sort of entire linked list. And of course you can use that begin function on that linked list returned to point to, so the iterator can point to that first node. So I have that in that PDF as how to actually do that. So now I want to go ahead and go over, well, how do we actually do this algorithm to find ancestors? So what you want to do is you want to find each node's ancestors. So you want to first sort these nodes 0, 1, 2, 5, 0, 1, 2, 3, 4, 5, 6, 7. You want to sort them alphabetically. So of course, actually, I think if you sort alphabetically, then 1 would come first, right? Because if you sort the string 1, you have sort these strings first. You would have 1 would go first, right? And then you'd have let me see. Oh, actually, no, I think hold on. Maybe 4 would go. No, I think 5 goes first. What am I talking about? Why am I okay? It's 5 would be first, obviously, then 4, and so forth, because we're gonna sort them by alphabetical order, not by actual number. Like 0 would be first, obviously, but 0 starts with letter Z, so that would not be first. So you have to sort these sort of by name. That's not hard. So the first thing we'll do is, okay, fine. You want to find all the ancestors of 5, but before we even do that, we're gonna have to first start this DFS on a node that actually has no ancestors. So in this graph, we can see here that 0, 1, and 2, these 3 nodes have no incoming neighbors. So you have to figure out which nodes have no incoming neighbors in your graph. So that one now lets you kind of think of the logic. It's not anything super bad. Of course, you can use as many data structures as you want to work this out. So you have to first figure out that these 3 are sort of they have no sort of ancestors. So okay, fine. So the first thing you have to do is you have to basically know that you have to sort this array by name. And of course, the first name you're going to look at is 5. That's the first name you're going to be working with. So I want to find all of node 5's ancestors. So obviously we can see here the ancestors would be these nodes right here. I think that's it, yeah, because 3 goes to 5, 0 and 1 both go to 3, so these 3 nodes would obviously be the ancestors of 5. You want to output them also in sorted order. So of course you output first 1, then 3, then 0, because that would be the sorted order. Now we're doing it sorted because it will sort of help code grade be able to grade everything, because obviously if you have it all different orders, then code grade will mess up. So sorting it and then outputting like that will make it so everyone's output will be the same, so code grade can handle all that. Okay, so you first want to find all of 5's sort of neighbors, or sorry, ancestors. So you're going to have to use a visited array. Now your visited array is going to be simple. It's going to be just basically standard unordered map, and I'll sort of put on a separate line over here, standard string bool, and then I guess I'll put on a different line here, visited. So just like that visited array that we covered for DFS traversal in class, except that we're going to use a string that's going to map to true or false. So true meaning that this node has been visited, and false meaning this node has not been visited. So obviously, if for the first time you search for a string in this visited map, it will return false by default. If it contains true, that means you have to have manually wrote true to that sort of node's string, which denotes a node name's value field. Okay, so of course we're going to have our visited array, and you may have to use another structure as well. You may have to use other structures as well on top of that to maybe make this work a little better. So of course, the first thing you have to do is when you traverse through all of these neighbors, or all these nodes, you got to find the first one that has no incoming nodes. So of course, you're going to have all these sorted already, basically. So of course, you first look at 5. 5 has an incoming neighbor. Then you look at 4. It has an incoming neighbor. And then, I'm trying to think, so after F, I think then T comes next. So then you look at 3 next. 3 has an incoming neighbor. Actually, no, sorry. After F, you look at 1. My mistake. So you first look at 5. Be first in the alphabetical order. Then 4. Then I'll say 1. So if you look at 1 next, okay, 1 has no incoming neighbor. So you're going to start your DFS traversal from node 1. Okay, so of course, as always, you're going to first start here, and use that same DFS code that I sort of gave you. Same logic, except you're going to iterate through and a linked list using that unordered map. So using that one code I provided for you on the handout, you're going to sort of use that. So of course you first start from 1. Look at all of 1's neighbors. Our first neighbor is going to be 3. We haven't seen 3 yet. We go over there, and then from 3 we try 7, let's say, and then 7 hits a dead end. So what's going to happen is, what I would do in my program is, well, I'm going to return false if I hit a dead end. So false would imply that, well, this path didn't lead to that relative named 5. So return a false, meaning, okay, that way was a failure. Okay, so let's try a different neighbor. Let's try 6. So we got to mark 6 visited, and 6 had no way to actually get to, didn't actually reach any, hit a dead end. It didn't reach 5, so of course return false, because from 6 we were not able to find a node 5 along that path. Okay, fine. So now we're going to try node 5 next, and now we see that, so we're going to have a current sort of, when we go ahead and call a DFS, we're going to have a current, of course. So of course you can use the DFS code I gave you in the handout, or sorry, not handout, in the notes, except you may have to have maybe more than just, you can have obviously a current going to be in this. I mean, I'll write the what's it called, the prototype right below actually in a second. But anyway, we're going to look at this node here, and we saw 5, and we are at node 5 now, so return true, which implies that, well, we successfully found it. So of course, if we return it true back, that means we're going to mark this node as an ancestor. We're going to mark that node as an ancestor. So I don't know, it's a big hint that we're going to use a hash map and mark, we're going to have 3 equal true, not in our visited hash map, but a different hash map we're going to have that marks that this node was, this node is actually going to be an ancestor of 5. Okay, so now we're going to return true back to 1, implying that, from 3 we found a successful search. Okay, so if true is returned back, well then mark this one also true, which means that now we know for 5 we have 1 and 3 are going to be ancestors. And then of course we want to start DFS again, because there could be more ancestors for 5, because we have to go ahead and now try, we have to go ahead and try DFS traversal from node 2, because that's our other node in this graph that has no incoming neighbors. And then of course you have to try DFS on 0, because 0 has no incoming neighbors as well. So you want to have a combined list, or this map that contains all of the nodes that are marked as ancestors of 5. And of course, once you have all those nodes in some type of a unordered map, you want to retrieve them, and then of course maybe insert them into a vector and sort that vector, and then simply output sort of all of the ancestors. So of course, let me go back to the PDF. There's YouTube. Wait, what's on right now? I think it's Tomb Raider, but I'm not really watching it. This is on right now because, well, I don't know. Actually, for me, I just have a TV on while I'm working on stuff. I don't always watch the actual TV. I just have something on just to help me kind of focus. So I don't know, maybe you guys do the same thing as well, but that's what I do to help me focus, just have something on. So even if it's not anything good like Tomb Raider 2, I don't think that was a good movie. It's something is on just to kind of help me focus. So that's my way of working, I guess. So I have this given to you right here. So this function sort is part of the algorithm library. And if you have, let's say, a names, which is going to be a list of names, if you go ahead and pass names.begin, names.end, it will just magically sort this list for you. So of course, use the sort function because it's there for you. So it makes your life a lot easier. Now also, I didn't put an image right here at the very top because it came out so nice. It was the first page has all the actual content, page 2 has sample output, and then page 3 has, so it came out nice. I didn't want to mess up that sort of that equilibrium, so I just didn't put an image here. But anyway, for a sample run of this program, enter file So you enter the file name right there. So the first name is 5, and here's a list of ancestors of 5, output in sorted order. Then you want to output next relative name, which will be 4, which is the next sorted ancestor name. Here's the 2 ancestors of 4. Then you want to output 1, the next relative, in sorted order, and 1 has no ancestors, you output none right there. And then 7's next one in our sorted order. We have these 4 ancestors. 6 has these ancestors, these are also sorted, and so forth. So we have to go ahead one by one, find a list of each ancestor, but these are going to be sorted. So 5, 4, 1, 7, these are sorted. And then the actual list of the ancestors of each relative is also going to be sorted. So that way, it'll make it easy for CodeGrade to verify your program. So let's see. So that's going to be that. Now I'm going to go back and just sort of give you the pseudo, or the not pseudocode, the what's it called? The function prototype for what you're going to want to have. So now it's up to you how you do this, but obviously this may help you a little bit. So let's go back to the OneNote. So of course, yeah, just to recap, you have to go ahead and run DFS on 2 and then on 0, output all the relatives, and you're going to have to clear all of these out, clear the visited array, clear the ancestor array out, and start all over again on a different ancestor. So of course, then you would have to now look at, not ancestor, sorry, a different relative name, and now try to find all the ancestors of the next relative in the sorted order, which would be 4 would come next. So of course, now you would try 4 next, and then of course, look at every ancestor of 4. So for my function I wrote, I had a Boolean function. I called it, what did I even call this? Let's call it ancestors, is what I used. And I would pass in standard string current, which is really the same exact parameter name like in our DFS traversal, that DFS that I went over in class. And then we're going to have another string, standard string, I'll call it search name. So when we call this function, obviously search name, we're going to pass in 5 into the search name, because we're looking for 5 initially. And current, when we first call it in main, current is going to be 0, 1, or 2. So at first it'll be 1. Then we call DFS again, but we're going to pass in 2 as current. So we're going to, of course, the node that has no incoming neighbors will be our starting point. And of course, you may have to run DFS more than once because of this graph. And of course, you have to run DFS all over again for a different search name, if that makes any sense. So then, of course, I'm going to pass in standard unordered map. It's going to be our graph, basically. Standard string. Then, of course, we're going to have list. So remember, it's going to be just an unordered map that maps to a list. I'm going to call this maybe just fam tree. And of course, we're going to pass in a standard unordered map. A lot of standards to write here, but I guess since we are using STL, it does make sense. String bool ampersand visited, because we are going to update visited in our traversal. And then of course, I guess I'll give this one to you. We're going to also pass in an unordered map. So person's name. It's going to be a Boolean as well. I'll call it maybe just list of ancestors. Let me go ahead and highlight, because I think it's really impossible to really see what's going on. But we pass in a current, We pass in our search name. We pass in our adjacency list, our visited array, and a list of ancestors. These are 4 things we pass. And of course, you can make yours different. You don't have to, copy this. But basically what I do is, of course, one of our base cases, if current equals search name, then we found our elements. Of course, we're going to return true. And then our other functions, when we're calling DFS, remember, we have to call DFS in that loop that goes to every neighbor of current. If a true is returned, then we can assign, we can add, we can look at list of ancestors, index current equals true, which means that this element is a proper ancestor of search name. And of course, at that point, we still have to go through every single possible neighbor because, like, for example, right here, let's say from 1 goes to 3. Let's say a true is returned back. Let's say if 1 went to 4 and 4 also went to 5, then we have to also mark those elements as ancestors as well. So you have to call DFS on every single possible node. But if all of them return false for a given node, then we can't mark this node as an ancestor. And of course, we have to call DFS again on the other nodes that have no incoming neighbors. Then we output all of those ancestors. And then we have to again do that same process all over again, but on 4 this time. So you have to again call DFS on 1, then 0, and then 2, and then find all the the nodes that can lead to the node 4 in this case. So of course 4 has ancestors 0 and 2 because 0 and 2 both go to 4 like that. So I hope this video and this this function prototype sort of assisted you with all of this. So of course there's no memory leaks to check for in this assignment because it's using all STL. And I use this file as one of my code grade tests. I have another file as well that I use, and that one is based on the Simpsons sort of family tree. So I kind of somewhat did it on the Simpsons basically. Now, it does make sense for the most part. Now, there's actually one case where I have it where Maggie is an ancestor of Mr. Burns. That's because Maggie owns Mr. Burns. I mean, if you saw the episode of The Simpsons, Maggie owns Mr. Burns, so she will be an ancestor of Mr. Burns. Other than that, though, it's just another example. And that one, I believe also, Jebediah Springfield is an ancestor of everybody because he was the first Springfielder. Is that the right? I'm going to say Springfielder. Yeah, let's call it that. So basically in that graph, then there's only one node. There's actually only 2 nodes that have no incoming neighbors. One of them is going to be, I believe, Jebediah, and I think Mrs. Bouvier, Marge's mother, are the 2, I believe, in that one. So of course you have to upload this to code grade, and that's basically it. So hopefully this video helped you out. So I guess happy coding, and till next time.